let's take a look at lesson 3.4, do a quick review for that. We moved from lesson 3.3, which was using derivative formulas to calculate the derivative, back to reminding you in 3.4 that a derivative is a rate of change. It really is measuring. One of the key ideas of a derivative is to measure how fast, increasing, decreasing, right? When it equals zero, how fast or when the rate of change of a function is equal to zero, or what its value is. We're interested in functions that represent things in our world, and that the derivative then has a very important meaning, some context, especially in physical sciences or biological sciences, engineering context, business context, that derivative means something. That derivative, again, the slope, the value of the slope at some point, or the general formula to find the derivative of any function at any point. And we started that with a limit, right? We defined it from the origins of using the way we were doing is finding how close, what is the slope between 2 points as they get closer and closer. And so we were able to find the derivative at a point, right? That instantaneous rate of change. And so we're being reminded in 3.4 of that, the importance of that, right? And as you can look at, as we think about that, one of the contexts that comes up is velocity, or the position, right, of an object that is moving. So there are many physical things and that move in the world. How do we know how to get a satellite to space? How do we know how to send something to hit the space station, even getting to the moon, right? How do we know that? How do we know the trajectory, right? All that would be guided by some mathematical functions, formulas, equations, right, of a position function. When you know the location of an object at a given time, if we know that, the derivative of that function is its velocity, and then the derivative of velocity is acceleration. Now, there's a difference between velocity and speed that you want to make sure we understand. Velocity is how fast the object's moving, right? Whether it's in a positive or negative direction. The negative tells us the direction. The speed tells us the absolute value of that, meaning that we don't care whether it's moving in a positive or negative direction. All we care at that is what is its speed, how fast it's moving. So you'll see this notation, absolute value of velocity. So in the text that you read in examples, you can see the examples. Again, a ball falling, we know its position. It's guided by science equations, math equations about the location of object that falls from space, a free fall it's called, right? And we can calculate how fast it's moving and so forth. So again, so this in this 3.4, we emphasize that relationship between position, velocity, and acceleration, right? And you'll see that language. So I want to make sure, and these are classic calculus problems. Keep in mind that the velocity, right, or the rate of change, or the position doesn't have to be a physical object. We can talk about population, right? You can have the position, your population be kind of like your position. And so you can see, we could use a rate of change formula at a point, right? Or if we know the function, then we can determine that. Another application is cost and revenue, and the relationship between that. So one of the homework questions involves this here. And so I know I have a reminder in the homework of 3.4, my homework notes to you. And I hope that you're finding those useful in some way. And of course, they're meant to guide you when you get stuck on the homework. And so you can see we went from the limit definition of calculating, like what's the derivative of a function, right? To, there's an example of it, right? To using those formulas in 3.3 as you do that. So that's what 3.4 is really, this emphasis on derivative as a rate of change and how it applies to many aspects of the world. And of course, these are just some of them. There are many others that use the derivative and rate of change idea.